artificial intelligence has grown massive. The models powering the best tools today are so enormous that their logic, the billions of individual settings that help them calculate a response, can no longer fit onto a single rack of computer chips. When tasks get too big for one station, history points to a simple solution: the assembly line. You break the work into small steps and pass it down the conveyor belt. This setup is often called pipeline parallelism. You split the AI's instructions across several physical racks of chips. Your request enters rack 1, gets processed, and is handed off to rack 2, moving rack to rack until the answer is complete. It sounds like a perfect plan, but AI pioneer Ilya Sutskever warned against it. He observed that when you look at how these systems actually perform, this assembly line approach is often a mistake. An assembly line works for building cars because metal is physical. But when we tried to apply that same logic to how software processes information, the system starts to choke. When your question enters the first rack, it's the only one working. While it processes your request, the other 3 racks are just waiting. This empty gap in the schedule means most of your hardware is doing nothing for most of the time. You have a fortune in high-end computer chips sitting idle. Every second those racks wait for data to arrive is a second of wasted power and time. To stop the waste, engineers flood the conveyor belt. Instead of running one person's request at a time, they start hundreds of different users' requests simultaneously, packing them together to keep every chip busy. This technique is known as microbatching. By splitting the traffic into tiny, constant groups, the factory finally looks efficient. Every floor is lit up and every chip is working. However, forcing the chips to run at maximum capacity this way creates 2 new problems that are much harder to solve. By solving for hardware efficiency, we've inadvertently created a massive traffic jam in the system's memory. The first problem is the commute. After each step, the AI moves its data across these physical blue cables to reach the next rack. Moving data through a wire takes a fraction of a second, but when the AI has to do this for every single word in a long response, those fractions add up, and the user feels it as a slow, stuttering output. Then there's the heaviest burden of all, the conversation notes, often called the KV cache. This is the AI's short-term memory. It's a record of everything said in a conversation so far. To pick the very next word, the AI has to reread all those notes every single time. Remember, we flooded the factory with hundreds of users to keep the chips busy. Now, every single floor must store the conversation notes for every one of those users. The filing cabinets multiply until they are literally crushing the floor space. We divided the AI to save space, but we ended up with no room at all because the conversation notes became too heavy to carry. The assembly line process is a trap. Any room you save by splitting up the AI's logic is immediately taken over by the exploding memory needed to manage all that traffic. It's like trying to fix a traffic jam by making the highway longer. It doesn't clear the road, it just puts more cars in the system. This is why the world's leading AI labs are moving away from the assembly line. Instead, they use a design called a scale-up domain. In this setup, massive groups of chips are wired so tightly they behave like one single unified entity. There are no floors and no handoffs. It's one massive open space where everyone can talk to everyone else instantly. Keeping the logic and the memory in one unified location removes the need for those slow, physical cable hops. It solves the space problem by letting the chips work together as one giant brain. When an AI answers you instantly, it's the result of this unified power. The assembly line is gone, replaced by a system where every chip is perfectly in sync.